In this video lecture, we'll be solving this problem, lowest common ancestor of a binary tree. So in this problem, we're given a binary tree and we have to find the lowest common ancestor of two given nodes in the tree. So what is the lowest common ancestor? It is defined between two nodes P and Q as the lowest node in the binary tree T that has both P and Q as its descendants. So there can be more than one nodes which has P and Q as descendants, but the LCA would be the lowest of all those nodes, and we allow our node to be descendant of itself. So we'll better understand these statements in the example. So in the input we will be given the root of the binary tree and two nodes P and Q for which the LCA has to be computed, while in the output we have to return an integer which represents the LCA for the given nodes P and Q. So let's see the constraints of the problem. The number of nodes in the tree will lie in the range from 2 to 10 to the power 5. That means the largest tree may have the number of nodes as 10 raised to the power 5. Then the value of each node may go up from minus 10 to the power 9 to 10 to the power 9, and all values of the nodes are unique, while the node P is never equal to node Q. So we always have two distinct nodes for which the LCA has to be computed. And the final condition is that the P and Q will always exist in the tree. Fine. So let's better understand the problem statement using an example. So here we have an example where we start by defining the LCA for two nodes P and Q, which is the lowest node in the given binary tree T that has both P and Q as its children. So here in this exemplar tree, we have P and Q as 5 and 1. So these are the nodes that we have given, and we need to find the lowest common ancestor for these nodes. Let's denote it by LCA. Stands for lowest common ancestor, and we want to find it for 5 and 1. And we can see that the lowest node which has both 5 and 1 as its children or descendants is 3, and hence 3 is the LCA for these nodes. Let's take another pair of nodes, say 7 and 2. So let's see the lowest node which has both 7 and 2 as its descendants. So we can see that 3 is the node which has both 2 and 7 as its descendants. 5 is another node which has 2 and 7 as its descendants. Then we have 2. It is also a node which has 2 and 7 as its descendants. Why? Because we know from the problem statement that a node can be a descendant of itself, and hence 2 is a descendant of 2, while 7 is a descendant of 2. Therefore, 2 is the LCA for 2 and 7, because 2 and 7 are descendant of 2, and hence the LCA for 7 and 2 is 2. So let's take another pair. What is the LCA for 6 and 4? So for 6 and 4, we want to find the lowest node which has 6 and 4 as its descendants, and that node is 5. Fine. So hence the LCA for 6 and 4 is 5. So that's how we check for the LCA for the given pair of nodes in the given tree. Now the next task is to find the solution to solve this. Let's build our solution for this particular problem. So the intuition to solve this problem is simple. All we have to do is just traverse the tree, and we simply check for each node whether it can be the lowest common ancestor for the nodes P and Q or not. How do we check that? Let's say we start from the root node, which is 1, where in this tree we want to find the LCA for node 9 and node 11. So we start from node number 1, which is the root node, and we ask ourselves whether this node can be a LCA for the nodes P and Q. For that, we know that P and Q must be descendants of node 1. So is it the case? And the answer is yes. We can see that if we traverse starting from node number 1 till these nodes 9 and 11, we can see that these nodes are indeed descendants of root node. All other nodes are descendants of the root node. Therefore, P and Q are descendants of root node. But that doesn't make it an LCA. The LCA must be the lowest such node which has both P and Q as its descendants. Now from 1 we have two options to move, that is 2 and 3. Let's move to 2 and ask the same question again, whether P and Q are descendants of node 2 or not. The answer is yes, both P and Q are descendants of node 2. So here again, now we know that this 2 is a children of the root node. Therefore, the root node is not the LCA for P and Q, because we have found a relatively lower node than the root node which has P and Q as its descendants. Then we check for node number 3 and we can see that P and Q do not exist in the subtree of the node 3. Therefore, this node, that is node number 3, cannot be the LCA for P and Q, and hence this entire tree is out. We do not have to consider the remaining nodes. That means we'll find our LCA in this subtree, and till now we have 2 as our common ancestor, but now we have to make sure whether it is the lowest common ancestor or not. Then we move to node number 4 and check if we find both nodes P and Q in the subtree of this node or not, and we do not find node Q in the subtree of node 4. Therefore, node number 4 is not the lowest common ancestor. Then we move to node number 5, and same is the case with node number 5. We do not find both the nodes in the subtree of the node number 5. Therefore, 5 is also not the lowest common ancestor. And since these nodes are not LCA, therefore both these subtrees are out, and we know that our LCA would be this node, that is node number 2, and hence the LCA for 9 and 11 would be 2. Fine, so that's how we used to solve this problem. So the next question is, how do we approach this problem? So observe one thing. For the lowest common ancestor, we find one of the nodes in the left subtree and another node in the right subtree. So what we can do, that we can simply call a function, let's call it a DFS function, in the left and right children for each node, which simply returns me whether one of the P and Q exist in that particular node or not. If it exists, then the DFS function returns true, otherwise it returns false. So how it will help us to build our solution? So let's see how we can solve this problem using depth first search. So we solve this problem using depth first search. So what is depth first search? Depth first search is a graph traversal algorithm or a tree traversal algorithm, which is a recursive algorithm, and it is used to traverse the given tree in a recursive manner. And it simply starts from the given node and it traverses the given tree in the depth first manner. That means it goes all the way down till the leaf node, and then it backtracks to the previous nodes so as to traverse the other branches. So it goes deep down till we reach the leaf node, then it backtracks to the previous nodes so as to explore the other branch. So this is the strategy for the depth first search. If you want to learn more about the depth first search, I will attach the resources to learn this algorithm in the description below. But I'm assuming that you have basic idea of how depth first search works. So let's see the working of the algorithm for finding the LCA using depth. Okay, so let's understand the working of this algorithm. So we define this DFS function, which takes in the current node on which we are standing and the nodes P and Q for which you want to calculate the LCA, and it simply returns true if you find P or Q or both in the subtree of node which is the current node. Even if we find P or we find Q or we find both the nodes, then this function is going to return me true, otherwise it will return false if we do not find any of the nodes in the subtree of the current node. So we call this function for the root node 3 here, and this function is called for DFS. Fine. And since we know that DFS works in a recursive manner, we first check whether there is a left child for node number 3 or not. So there is a left child, and hence the DFS function will recursively call itself for the left child. So DFS, then again the DFS function will be called for the left child for node number 5, that is 6. So here you see that we have found node P here. Since we have found one of the nodes, then that means this function will return true to its calling function. So it will return true to this calling function to this node. So true will be returned from here. Then this will again return true to the calling function. So it will be returned here. And then we recursively call this function DFS for the right child, that is here. So this will be called for DFS2. But since we know that the node Q does not exist in this tree, in this subtree, then this function call is going to return me false. And hence we conclude that in this subtree of the node number 3, we have one of the nodes for which we want to find the LC, and that node is P. Then now here we have true, then we call the DFS function for the right child, that is this one. So DFS is called for node number 1, DFS. Then that function will be called for the left child, that is for this node. And because first we explore the left child, then we explore the right child. So and here we find the node number Q. So the node number Q is found here. So we return true from here. True is returned from. Then the function will be recursively called for the right subtree, and this subtree will return false. So we have false here, we have true here, and here again this subtree also returned false. But since we know that we have found one of the two nodes in this subtree, we have to return true from here. So that's why we got true here. Here again, since we have found one of the nodes in this subtree, we have to ignore this false and we return true from here. So I'm getting true for the left subtree and a true for the right subtree. That means I have found one of the descendants in the left subtree and another descendant in the right subtree for the node on which I am standing, that is node number 3. And hence this is our LCA, and hence LCA for 6 and 0 would be 3. So that's how this function will work. How will the body of this function look? So this is just a DFS, and we just have to modify our depth first search algorithm a little bit so as to obtain our final result, which is the LCA for the given two nodes P and Q. Let's move on to the implementation part. We will be implementing this DFS function. So here is the implementation part. This is our function which takes in the current node on which we are standing and the two nodes for which we want to find the LCA. So this is the base case where we check if we have reached the leaf node. So if we have reached the leaf node and we haven't find our descendant nodes, then that means we will return false. Otherwise, we will recursively call the function for the left subtree here while passing the left child of the current node and the descendants P and Q. Now if this function call returns me true, then that means in the left subtree we have our one of the descendants, and hence 1 will be stored in the left child. Otherwise 0 will be stored. That means we do not have any of the descendants in the left subtree. Same goes for the right. If we find one of the two descendants in the right subtree, then 1 will be stored in this right variable. Otherwise we'll get 0 here. Then here we are handling the case where one of the two nodes is the descendant of itself. That means the two nodes are connected by a single edge. For instance, P and Q are here. For instance, if we have P and Q as 3 and 6 for this tree, that case is handled if the current node is either equal to P or the current node is either equal to Q. If that is the case, then we'll store 1 in this mid, otherwise we'll store 0 in this mid. And here we have 3 cases. If we have found our descendants in the left subtree and in the right subtree, then this will give us 0 plus 1 plus 1, that is 2. So this is one of the positive case where we have found our LCA. Another positive case is that if the two nodes P and Q are simply connected by a direct edge, in that case one of these two variables left or right will store 0 and this mid variable will store 1, because current node is either equal to P or equal to Q. Fine. So there can be 2 cases corresponding to that case. So this is the first case where we have found one of the descendants in the left subtree, but we haven't found another descendant in the right subtree, but the current node on which I am standing is actually one of the descendant. If that is the case, then corresponding to that case we'll get this type of configuration. While we may find our one of the descendants in the right subtree and not finding it in the left subtree, and the current node is equal to the another descendant which we haven't found in the left sub, and corresponding to that case we'll have, so if we encounter any of these cases, then that means the current node is the LCA for the nodes P and Q, and hence we store that node into our answer variable. So we declared this answer variable globally. Then there can be a case where we just find one of the descendants in the given subtree. So either it is found in the left subtree or it is found in the right subtree, or the current node is one of the descendants. If that is the case, then we return just true from here. While this is not the answer but one of the descendants, while this is not the answer node lies above the current node. So that is the case that we are handling here. So that's how the function is working. Let's analyze the time and space complexity. So you can see that we are just performing a normal DFS, and the time complexity for the depth first search is big of n represents the number of nodes in the given tree, while the space complexity for the given recursive solution is constant because we are not using any auxiliary space. Although the stack space is consumed, the stack space is linear, but the auxiliary space is constant. So let's move on to the code implementation part. So this is the solution class, and this is our definition for the tree node. In the tree node we have a value, we have a pointer to the left subtree, pointer to the right subtree. This is the constructor which is used to initialize the values for the data and pointers. Then we initialize our global variable answer, which will store the final LCA for the given nodes. Now, this is my recursion tree function which takes in the current node and the descendant nodes P and Q and checks if current node is the LCA for P and Q or not. Then I have my lowest common ancestor function which returns the LCA for the nodes P and Q, and it takes in the root of the given binary tree. And here I am calling this recursion tree function. So this recursion tree function will simply evaluate the answer. So here we are handling the base condition. If the current node is the leaf node, then we return null from here. Otherwise, we call the same function recursively for the left subtree and right subtree to check for the existence of the descendants in the given subtree. And then here I'm handling the condition where there is a direct edge between P and Q, where there is a direct edge between P and Q. Then I'm checking if the current node is the LCA or not. If it is the case, then I store that current node in my answer variable. Otherwise, I'm simply returning if I find one of the descendants in the subtree of the current node or not. So this is how this function is working, and this is the implementation in C++. Let's see the implementation in other languages. So I've attached the codes in the description below, so make sure to check it out. And that's all for this video. If you like the video, then do like it and make sure to subscribe to my YouTube channel and give your feedback in the comments below. I will see you in the next video. Till then, take care. Bye bye.